Welcome back to my channel. In this video I'm going to analyze the PlayStation 5 motherboard and how you can repair it on component level. Keep in mind that we can't always fix the PlayStation 5 because we don't have schematics. We don't have the software to pair some dedicated integrated circuits like the APU and the disk drive board IC. Also, some ICs are expensive to replace like the Southbridge IC. Before we going to start, I would like to thank you all for your support. The channel is slowly growing and the feedback that I'm getting is really appreciated. So thank you all for subscribing. So let's start. So this is the flow diagram that I'm using to troubleshoot the PlayStation 5. First is when you press the power button, there are two conditions. The first condition is that you have sound and light indication. The second one is there is no sound or light. When you have a no power condition, first that I do is to check the SMPS power supply, if it is any good, if it is outputting 12 volt. If the power supply is okay, then we can check further. We're going to check the boot sequence. And if that is okay, then usually, yeah, you have a working PlayStation 5. So in most cases, the sequence is not correct. Then we're going to check the standby voltages, the power on voltages, and also check the Southbridge IC. So the second scenario is that you have sound and light. Then you have two situations. One, it stays on the PlayStation 5 or it turns off. When it stays on, if the LED is blue, then you have to check all the power on voltages, the solid state drive controller, the memory and the APU. And if you get a white LED, then you have to check if there is a picture on the screen. And if you don't have a picture on the screen, then you have to check the HDMI encoder IC and the connector. In a situation that it turns on and then off after a beep or 3 beeps. So after 1 beep, if it turns off, yeah, also check the standby voltages, check the power on voltages. If you are getting 3 beeps and then off, check the BIOS firmware. Also check the Southbridge IC. So these are some general indications where to look for any problems. The most difficult condition to troubleshoot is a blue light of death. A blue light of death is a condition that the PlayStation is on and it's pulsating a blue light and it never goes to a white light. In that situation, the troubleshooting process is more difficult. The problem can be everywhere. Can be the SSD, can be the RAM, can be an APU. And when the blue light is pulsating, it also means all standby voltages are present, all power on voltages are present. So most of the time it's a bad APU, a bad RAM module, a bad SSD module, or the controller. So a blue light of that is really difficult to troubleshoot. So this is the main motherboard of the PlayStation 5. This is the front side. As you can see, this is the HDMI connector. This is the HDMI encoder IC. Then we have the Ethernet connector. These are the two USB connectors. These are located on the back side. And then we have the back side of the Wi-Fi Bluetooth IC. This is the BIOS IC or the NOR IC. This part is where the Southbridge IC is located. The Southbridge IC is an IC that often goes bad, and this IC is expensive to replace. So this IC is currently about $50 to replace. This is a speaker. This is the power management area for the Southbridge IC. It generates different power rails. This part is the generation of the Vcore power rail that goes to the APU. So this is the APU. Then we have two regions where the power rail for the memory is generated, the Vmem. It's 1.35 volts. Then we have the 12 volt input connector. So the power supply will be connected to these two pins. This is the plus and this is the minus. And it will deliver 12 volt. Here is some power management regulation. Then we have the SSD region. So these are the NAND flash memory. And this is the controller. Then we have the 3.3 volt battery for the real-time clock. And as you also can see here is that all those data lines that are coming from the APU are going to the memory modules. Also, the USB connection goes straight to the APU. Also, the data lines for the SSD go straight to the controller. So these are the important parts from the front side. This is the back side of the main board. This is the front side for the Wi-Fi Bluetooth module. So that's in this region. Then we have the LED connector. So the ribbon cable that goes to the LED connects to this connector. Then we have the fan connector. So when you have a CD drive, there will be a connector here for the CD Blu-ray drive. This is the backside of the Southbridge area. This is the crystal oscillator. It will generate a clock signal for the Southbridge. And then we have some power regulation going on here. Here is also some power regulation going on. This is the backside of the Vcore power regulator. So it also generates the Vcore for the APU. This is the backside of the APU with lots of decoupling capacitors. These are the RAM modules. So this is a power regulator that will generate some power rails for the SSD controller and also the memory modules. So this is the backside of this SSD controller. So the SSD controller is located here, and these are the flash memories. Here you can add some external storage. This is the power button connector. So the ribbon cable that goes to the power buttons on the front panel is connected to this connector. So these are the most important sections of the backside of this motherboard. We are now going to take a look at all the standby voltages. So standby voltages are generated when you plug the power cable into your main power socket without turning the console on. It will also generate some standby voltages in the background. If there is a standby voltage missing, the console will not turn on. In standby mode, the Wi-Fi module, the Southbridge IC, the SSD controller and the BIOS needs power. In standby mode, if the power doesn't reach one of those areas, the console will not respond. When you turn on your PlayStation 5, the power supply will deliver 12 volt at this connector. So when the console starts up, the power supply should deliver more than 30 amps. So if you have a lab power supply that doesn't deliver 30 amps, you cannot use it to turn on the PlayStation 5. But you can use your lab power supply to test it in standby mode. So in this region, the 12 volt from the power supply reaches this power regulator. This regulator will convert the 12 volt into 5 volt. I call it 5 volt standby. And from the 5 volt standby, the different power rails are generated. So from 5 volt, it will generate somewhere on the board 1.8 volt, 3.3 volt, 1.1 volt. But these power rails are all generated from the main power rail of 5 volt. This power management IC is a TPS 53219A. This IC is responsible for generating the 5 volt. Next, on this power regulator, the 5 volt standby comes in and it will generate a 3.3 volt standby. So in the next slides, we will zoom into these regions to see it more clearly. So this is just a general presentation about where to probe the standby voltages. So in this region, we have the voltage regulator for the Southbridge IC. So it will generate 1.15 volt, 3.3 standby volt, 1.9, and also 5 volt goes into this IC. And this IC is a Dialog power management IC, a DA9065, and this powers the Southbridge IC. And on pin 27, we can also find 1.8 volt standby on this IC. On this pad, we can also find 5 volt standby. And in this switching regulator, if I'm correct, it should also give 2 volt. Only I don't know if it is in standby mode or in power on mode. That's why it's in red. So you have to check if this power rail is present in standby mode or in power on mode. When you have a short on the 12 volt rail, you can try to isolate the problem area. So this is the region where the Vcore power rail is generated. On the left hand side we have the 12 volt. And on the right side it will go to the regulator of the Vcore power rail. So to test if the problem is on the left hand side or in the APU side, we can remove this coil and probe where the short is. So we can probe it here to see if it's in this region or in the APU region. So we can put the multimeter in diode mode on this pad, but remove this coil to separate it from the circuit. Here we can find the standby voltages on the back side of the mainboard. So in this region we have an SBV IC. It will generate 1.9 volt standby. 5 volt standby is coming into this regulator, and it will create 1.9 volt standby. In this voltage regulator, 5 volt standby goes in, and this regulator will create 3.3 volt. The same as here. On the upper pin of this IC, the 5 volt standby should be present. Also the 3.3 volt standby should be present in this on this pin of this IC. In this region we can find the 12 volt. The 12 volt is also present on these pads here. Here's the power button connector, and these two are the pull-up resistors. And on the top of this pull-up resistor we can find 3.3 standby voltage. When you press the power button, what will happen is basically the 3.3 volt is connected to the data line that goes to the power button. So when you press on the power button, this 3.3 volt will be shorted to ground. And that will create a pulse. That pulse will go to the Southbridge IC, and from there it will start to boot the sequence. So in the case that the 3.3 volt is missing, the console will not show any signs of life. So when you press the button, you will not hear the beep or see the lights, because the 3.3 volt is missing. That is responsible for generating the pulse to start the boot sequence. So when you press on the power button, the console will try to generate specific voltages that only are present when the console is turning on. So these are the locations that you can find on the front side of the mainboard. So 12 volt is always present. Then we have the Vcore of 1 volt. So the Vcore is generated in this region. It will convert 12 volt into 1 volt. Then we have two voltage regulators or switching regulators to create the 1.35 volt for the RAM. You can also measure the resistance on this coil. It should be around the 40 ohms, so it's really low impedance. On the back side, the 1.1 volt is created near the Southbridge region on the back side. That is here. On this voltage regulator, when you press the power button, the 2.5 volt will be present at this point. Also the 0.8 volt is present at the end of these capacitors. On the back side, these are the 1.35 voltage rail for the RAM. So you can measure it here. 12 volt is always present. And in this region, we can find the 5 volt. So the 5 volt power on voltage will be present at this point. The Vcore is present at this point. So yeah, these are the main power on voltage that has to be present. So if there is a voltage or power rail missing, you have to investigate further if there is a short on that rail and maybe inject some voltage to see which component gets hot. When you open up the PlayStation 5, check if the warranty seal is intact, because if not, then you know that somebody already opened the console. Also check if all screws are present and the correct size screws are in the right holes. Because as you can see here, we have long screws and small screws, but if there is a long screw in a location where there should be a small screw, it can damage the multi-layer PCB board, and then to fix that one is really difficult. So check all these points before proceeding. When you remove the housing and you have your main board PCB exposed, if you see any liquid metal on the PCB board, remove it with some isopropyl alcohol. Also look for hotspots on this area, because if you see a hotspot, it can indicate that the APU was getting really hot, and it can also be that the APU is then faulty. Also, this APU is paired on the board, so if this APU is faulty, you cannot change it with another one. Check if there is any rework done on the main board. Look for signs of flux, and if you see any signs of flux, investigate that area. Also check if the ICs are making a proper connection with the pads, and also if the pins are making a solid connection with the pads, that are not moving. And from there we can check the HDMI ports, USB ports, and analyze the main board further. This is a standby boot sequence troubleshooting chart. This is a chart that can help you identify the problem areas. You can use this chart when your PlayStation 5 does not power on, when you press the power button. What you must do is connect the PlayStation 5 to your lab power supply and set the voltage to 12 volt with the current limit of plus minus 2 amps. Connect the positive lead to the right side of this connector. Connect the black lead to the left side of this connector. Turn on your lab power supply. Also remember, do not power up the PlayStation 5 because this test only works in standby mode. When you turn on your lab power supply, you can monitor the current draw. In a healthy PlayStation 5, the current draw should jump to 321 milliamps and then settle down between the 7 or 10 milliamps. If you see this behavior, your PlayStation 5 standby is good. If you see a different behavior, you can compare the current draw with this chart and then try to identify the problem area. If you see a different current draw, like 0 amps and it stays on 0 amps, then you have to check the BIOS IC, the fuses on the PCB board. Also check if the 12 volt power supply is working and check for shorts on the 12 volt input. When you see a current draw of 15 milliamps and it stays on 15 milliamps, check if there are shorts near the Southbridge IC. When the current draw is 5 milliamps and it stays on 5 milliamps, check for shorts near the HDMI encoder IC. When the current draw starts at 7 milliamps and jumps to 27 milliamps and stays there, then you also have to check the Southbridge IC. When the console is stuck at 7 milliamps, you can check Dialog IC to check if the right voltages are present. Also check the crystal oscillators, if the frequency is present of 25 MHz. And also the 32 kHz clock. If that is working, try to see if the Southbridge IC is accessing the BIOS IC. So if you see communication going to the BIOS IC and from the BIOS IC back to the Southbridge IC. If you don't see any communication coming into the BIOS IC, maybe the Southbridge IC is faulty. And if you do see communication going in and out, the BIOS IC could be faulty or some corrupted firmware on the BIOS IC. So maybe you have to refresh the BIOS IC. Next, if you see a current draw of 7 milliamps, it jumps to 12 milliamps, back to 7 milliamps and then 12 milliamps. So there's a boot loop. Then you have to check for shorts on the 1.1 volt power rail. When the current draw starts at 24 milliamps and goes back to 7 milliamps, check for fuses and check for shorts on the board. When you see a current draw of 35 milliamps and it stays on 35 milliamps, then you can check for shorts on the 1.9 power rail. If you see a current draw of 58 and it goes back to 7 milliamps, also check the fuses and check for shorts on the board. When the current draw starts at 175 milliamps and goes back to 10 milliamps, then you have to check the SSD controller for shorts. When the current draw starts at 225 milliamps and goes back to 7 milliamps, also check the SSD controller for shorts. When the current draw starts at 270 milliamps and you press the power button and you hear a beep, then you have to check for shorts near the Wi-Fi IC. In the case that your current draw is stuck at 350 milliamps and it stays on 315 milliamps, then you have to check the 3.3 power rail if it's present, and also check for shorts near the Wi-Fi IC. So in the last case, when you have 321 milliamps and then it goes back to 7 or 10 milliamps, but when you compare it with the normal behavior, this takes a few seconds. But if it goes really fast back to 7 or 10 milliamps, then you have to check your SSD controller. Because if your SSD controller is bad, you can sometimes see a update screen or a no power behavior. So yeah, this is the last case that we can check. This is a Dialog power management IC. So this IC is responsible for generating different power rails. Most of the power rails will go directly to the Southbridge IC. So this IC is a DA90D65. So this is a power management integrated circuit, also called a PMIC, power management IC. So this IC has different buck converters to generate different power rails. This is schematic of a different IC, the DA9062. Because this IC don't have any data sheets, so we cannot compare it, but there are different buck converters that will generate different voltages. There are also some low drop voltage regulators to create some minor voltages, and this is basically the same for this IC. So if we zoom in, this is the Dialog power management IC. On this cap it will create a output voltage of 3.3 volt. So this is a standby voltage. 3.3 volt has to be present on this cap. On this cap there has to be present 1.9 volt. On pin 27 there has to be present 1.8 volt. The input of this IC is a 5 volt standby power rail. So all these voltages are created in standby mode. So these are the pinout for the Dialog power management ICs, and you can check the different voltages on each of the pins. There isn't much information about this IC and what each pin does. It can be that some of the pins are incorrect, but it's just an indication how you can troubleshoot or analyze each pin. This is a buck converter. So this IC is called the TPS53219A. It's a power management IC. What this power management IC does, it will create 5 volt standby power rail from the 12 volt power supply. So this is the buck converter. So this is the power management IC, the TPS53219A. And the main purpose is to generate a 5 volt standby power rail. And it will do that from the 12 volt power supply. So it will convert 12 volt to 5 volt. So here are the pins from this IC. So if we zoom into this data sheet, there are 3 important pins that we have to measure. So we have the enable pin on pin number 2. We have the switch pin on pin number 12 and the VDD, that's the power input, on pin 6. To troubleshoot this voltage regulator, check if the voltages on the pin marked in yellow are present. So the first pin is the enable pin. There has to be voltage present to enable this IC. The next pin is the switch pin number 12. There has to be a 5 volt present at the output. And this IC also needs power to operate. And the power comes into pin 6, the VDD pin. So when these voltages are present, you can conclude that this IC is working perfectly. The PlayStation 5 has a Southbridge IC. So this is how the IC looks like. It starts with CXD 9006. The Southbridge is a low speed component that manages the input and output functions of the console. It communicates with other components that also are located on the PCB. The Southbridge also communicates with the BIOS IC, and the Southbridge also generates the clock signal. This clock signal goes to the BIOS IC. Also the Southbridge sends data to the BIOS IC, and also the BIOS IC sends data back to the Southbridge IC. When you press your power button on the console, the signal goes directly to this IC, and from there it will start a boot up sequence, a startup sequence. Some of the key components of the Southbridge include a network controller, audio processor, storage controller, USB controller, security processor, power management, thermal management, And if you have problem with your Southbridge IC, can relate in symptoms like no power. Testing the communication between the Southbridge and the BIOS involves checking different pins at the BIOS IC. The BIOS IC has a power pin, a ground pin, some data pins, and also a control pin. Probing the data lines of the BIOS IC involves using an oscilloscope to monitor the data signals on the IC data pins. The data input pin receives the information from the Southbridge, so from the Southbridge the information goes to this pin. The data output pin sends the information back to the Southbridge. This is the clock pin. It is often labeled as CLK and serves as the input for the clock signal that synchronizes the operations of the BIOS chip. So the clock signal plays a vital role in coordinating the data transfer between the BIOS and the Southbridge. Data must be sent and received at the right time, and the clock signal ensures this synchronization. So the clock signal typically comes from an external clock source, such as a crystal oscillator or an external clock generator circuit. So in combination with the Southbridge, it's the responsibility of the Southbridge to send this clock signal to the BIOS. So the clock signal comes from the Southbridge and goes into this pin. The BIOS IC itself doesn't generate its own clock signal, so it relies on an external source to provide the clock signal for its operation. Then we have chip select pin on pin 1. The primary function of the chip select pin is to enable or disable the BIOS IC. So when this chip select pin is asserted, so it is active low or active high depending on the chip design, it allows communication with the BIOS IC. So when this chip select is a low, then communication on the data lines is possible. When this chip select signal goes high, then the communication between the data pins is not possible. So when the write protection pin is asserted, it activates the write protection feature on the BIOS chip. So in this state, the write operations to this BIOS IC are typically disabled and the BIOS firmware becomes read-only. The VCC pin provides the necessary voltage to power the BIOS IC. This voltage is 3.3 volt. So to analyze the data on the data pins, what you have to do is you have to connect the probe of your oscilloscope to the data pin. So on data output, data input, or the clock signal. Then you have to configure your oscilloscope and display the signal on the selected data line. Also adjust the voltage scale and the time scale to view the signal waveform effectively. So you want to see this waveform on your screen. Next is to power on the PlayStation while keeping the BIOS IC connected with your probe. This will allow you to observe the data signal as the BIOS is accessed during the boot process. And you can monitor this signal waveform on the oscilloscope. You should see the changes in the voltage levels on the data line as the BIOS is read or written. So the signals will be in a form of binary data, so 0 and 1s. If you place your probe on the data input pin, you should see the incoming data from the Southbridge IC. Let's say this is the data input pin. You see the data on your oscilloscope, then you can assume that the Southbridge is trying to communicate with the BIOS IC. If you see the outgoing data from the data output pin going out, so let's say this is data output, and you see the data on your oscilloscope, then you know that the BIOS IC is answering or sending information back to the Southbridge IC. If you see the clock signal on the clock pin, then you know the clock signal is generated by the Southbridge IC. When the clock signal is missing, then you have to check the Southbridge and the clock circuit. When the data input signal is missing, then you have to check the Southbridge circuit. When the data output data is missing, check the BIOS IC or reflash the BIOS. If the 3.3 volt is missing, then you have to check the power rail for shorts, the 3.3 volt power rail. On the backside of the Southbridge IC, we have a lot of capacitors. Also check all these capacitors for shorts, because if there is a short here, then most probably the Southbridge IC is bad. Then we have a 32 kilohertz real-time clock. This is a clock signal with a frequency of 32 kilohertz. This specific clock frequency is commonly used for circuits for the timekeeping. The power for this crystal oscillator comes from the battery. And with an oscilloscope, you can probe this oscillator to see if the 32 kilohertz clock signal is generated. So if the 32 kilohertz clock signal is missing, then you have to analyze this circuit. When you power on the PlayStation 5, then the 1.1 volt is created on this inductor or capacitor. Close to the Southbridge, you have the 3.3 volt standby power rail that is generated in this location. So when we zoom in on this gap, there should be 5 volt standby present. On this inductor or a coil, there should be 3.3 volt generated, and the 3.3 volt standby voltage is needed for the data lines to generate a signal to the Southbridge IC. So let's say if you are missing 3.3 volt, the power buttons will not work. The Southbridge IC, the encoder IC, also voltage regulators, the power management IC, and the Wi-Fi IC will not operate. So 3.3 volt is a very crucial power rail. The Ethernet connector is located here. And when we zoom in, this is the Ethernet connector. And there's a component here. This is a cable interface. So a cable interface is to reduce the transfer of electrical noise and interference between different components or devices connected by the cable. So if a cable is connected here, this interface is used to reduce this electrical noise and all those interference that are present when you connect a cable to a connector. So this is a schematic of this component. And what you notice is that the wires aren't directly connected to the endpoint because they are isolated. And that is done to reduce the electrical noise. If you measure each pin with a multimeter in diode mode, each pin should be around 0.45 volts. Near the HDMI we have the encoder IC and also the voltage regulator that creates the 5 volt standby voltage. And as you can see here, we have a lot of measuring points where you can measure the standby voltages. So let's say on this IC, on this leg, there should be 1.7 volt present. On this pad, there should be 2.8 volt present. The output here should be 5 volt. So these are just some measuring points if you want to troubleshoot it in more detail. On the back side of the PCB, there's an IC called SBV IC. This is a power management IC. When we zoom in, this is the SBV IC. The 5 volt standby voltage goes into this IC, and this IC will generate a 1.9 standby voltage. This is a schematic representation of this IC. Every name marked in yellow are the most important pin to analyze with the multimeter. On pin 1 and 2, the switch pin, we should get 1.9 volt. On the power supply pin number 12 and 11, there should be the 5 volt standby voltage present. Also, there should be an enable signal to enable this IC. When the voltage is generated like 1.9 volt, this IC will send a power good signal. If you want to know what the difference is between an enable signal and a power good signal, the enable signal goes into the IC. So this enable signal can come from the Southbridge IC or it can be generated from the power supply. It's the input for this IC. So if this signal is present, this IC will turn on. The function of this IC is to generate 1.9 volt. And if the 1.9 volt is generated correctly, this IC will send a power good signal. And this power good signal goes to another IC, maybe the Southbridge IC. And when that power good signal goes into that IC, then it's called a enable signal. So the difference is enable goes into the IC, and if the IC is working properly, it will send its own signal, the power good signal, to the next IC. So here there is another voltage regulator. The input will be 5 volt standby voltage and its function is to generate a 3.3 volt. So when we zoom in on this pad, the 5 volt standby should be present. And this IC will generate a 3.3 volt standby. On the front side of the PCB there is a switching regulator located in this area. So when we zoom in on this pad, the 5 volt standby should be present, and also the 2 volt on this inductor should be generated. I'm not certain if this 2 volt is generated in standby or on power on mode. So you have to check for yourself if this 2 volt is generated in standby mode or in power on mode. The Wi-Fi module is located on the back side of the PCB board. So this is the front view. This is the back view of the Wi-Fi module. On the back side you see a lot of capacitors, and you can check these capacitors for shorts. If a capacitor is shorted or this Wi-Fi module is shorted, it will prevent the PlayStation 5 from booting up. And also check if the fan connector is not ripped. In this location we have 2 components, and on those 2 components we can measure the 5 volt standby and the 3.3 volt standby. On the first component, on pin 1, there should be 5 volt standby present. On the second component, on the bottom pin, there should be 3.3 volt standby present. Also you can measure the 1.8 volt standby on this capacitor, and on this pad there should be the 5 volt standby voltage present. So all these voltages have to be present in standby mode. The encoder IC is located on the front side of the PCB board. The brand of the encoder IC is from Panasonic. It's an MN864739. This encoder IC is responsible for processing video signals and converting them into a correct resolution to display the picture on a television or monitor. This also includes support for different video resolutions, refresh rates and color formats. When this IC fails, then you can get a no picture. So the PlayStation 5 turns on, you will get a white light, but you don't see any picture on your screen. It can also create a no power behavior. Or when you try to turn on your PlayStation 5, you get the blue light of that. So that is a pulsating blue light, but it never goes to a white light. It can also give a 2 seconds of that behavior. So after 2 seconds, the console turns off. When you get the white light of that, when you turn on your PlayStation 5, so everything seems to be working, but you don't see any picture. Check this HDMI port, also the nearby components. Check these data lines and filters, and also check the encoder IC. To check the HDMI connector, what you can do is you can probe each pin with a multimeter in diode mode, and every pin has a certain voltage. So you can compare the voltages that you are measuring with these voltages. And if you see a deviation, then you can troubleshoot the area. Also, there's a little capacitor here of 100 picofarad. There's a capacitor here of 100 nanofarad. This is a 5.6 volt Zener diode, and this resistor is 27K. When you replace this HDMI port, be careful not to knock off all those components here. When turning on the PlayStation 5 or waking it from sleep mode, the power indicator light on the front of the console turns blue, indicating that the console is powering up. However, instead of successfully booting up and displaying content on the screen, the console may get stuck with a solid blue light, or it may blink for an extended period without making it to the user interface. This blue light of death issue indicates a problem, preventing the console from functioning properly. The specific cause of the blue light of death can vary, but they are often related to hardware or software problems. These can include issues with the console, hardware components, power supply, or the system software. It may also be triggered by overheating or improper initial setup. The cause can be everything, and that is why blue light of death are hard to fix. So the blue light of that is also a generic error code. It keeps pulsating because it keeps running checks on the background, and those checks are failing, and it reboots these tests and it keeps repeating itself. So it will never go into a bootable state. If you don't find any shorts, all the standby voltages are present, all the power on voltages are present, then most likely the problem is with the APU or the RAM ICs. To troubleshoot an APU or the RAM is really hard and difficult. You could replace the RAM modules with known good ones. Maybe that solves the problem, but when all the voltages are present and there are no shorts, it's hard to solve these problems. Also, when you hear a beep every 5 or 10 seconds, it could also indicate a short on the board. When you try to update the console with a new firmware on a USB stick, but then the console gives an error like can't perform this action, multiple USB drives are connected, most likely your APU is faulty and not fixable, because when you look at these USB connectors, those data lines go straight into the APU. So when you have a fault with your USB and it generates an error message, then most likely it's not fixable. Near the two USB ports we have two ICs. These ICs are TPS 2001D current limited power distribution switches, and these ICs are there for protecting the circuit from overcurrent situations. We are interested in 3 pins: the enable pin, the input pin and the output pin. So measure if you have an input voltage and if you get an output voltage, and if the enable pin is on. When you turn on your console, the console should generate a Vcore of 1.0 volt, and the 1.0 volt is generated from the 12 volt. This is the location where this generation is taking place. So this is the front side. I think this is the back side. Here you have for every phase a VRM MOSFET driver. That is a NCP252160. Input of 12 volt goes onto this pad. And on these pads here, the Vcore output should be present. So 1 volt. Same as here. So on this pad, the Vcore of 1 volt should be present. 12 volts should be present at the left side of this coil and also on the right side of this coil. So these are the VRM MOSFET drivers. For every phase we have one MOSFET driver. It's an NCP252160. This is the schematic. This is the pinout. And we're interested in the pins in yellow. This IC needs power to operate, so that is on the VCCD pins or the VCC. And then we have the 12 volt input and the switch. So on the switch pin we should get 1 volt, the Vcore voltage. When you have a short on the 12 volt line, most probably one of those MOSFETs are shorted, and then you have to investigate which one. What you first can do is remove this coil and check where the short is located. Try to isolate the probe. So if it is on the left side or in the Vcore side, you can lift this coil and check if the short is present here or here. If the short is present in the Vcore area, the best method to troubleshoot is to remove each coil to see which phase is shorted, because these phases are all connected in parallel. If you see a short, it doesn't mean that it's present on this location. Could be here, could be here, could be here. And what we have to do is to isolate the problem. And we can do that by disconnecting all those coils and then measuring on each side where the problem is. And then you can inject some voltage and to see which MOSFET driver is faulty. This is the connector where the 12 volt power supply will be connected. So this is the plus side, this is the minus side. And in this region we have some voltage regulation going on. And when we zoom in, so this is the power connector. 12 volt goes into the mainboard. In this region there is some power regulation going on. These capacitors here often fails. So if you have a short, check this location first. Check the capacitors for shorts. Check the MOSFETs for shorts. Also check the continuity of these coils. So on the back side of the mainboard we have the GDDR6 RAM modules. So we have 8 RAM ICs and all these ICs need to have power. The power rail that will deliver the power to these memories is called Vmem. because we have two sectors, bank A and bank B, we have two voltage regulators that will create the voltage memory. So on the front side we have the power regulators for the GDDR6. So this is the voltage regulator for bank A or bank B, doesn't matter. And the second one is here located, is the GDDR6 power regulator. So we have two power regulators that will provide power to the RAM banks, bank A and bank B. So when we zoom in, so this is the voltage regulator one that will create a voltage memory of 1.35 volt. And this power will only be generated when you power on your console. So for the second voltage regulator that also creates voltage memory 1.35 volt, is located on the other side. It has the same layout as this voltage regulator. Also the MOSFETs have the same part number. These two voltage regulators will create the 1.35 volt. Yeah, if you want to know what the impedance value is of this coil, because this is the output, this is also the output, what you can do is you can put your multimeter in resistance mode, put the black probe to ground and the red probe to this pad of this coil. This is the output for the power rail that goes to the memory banks. When you measure the resistance, it should be around the 40 ohms. If you see a lower value, then that can indicate a problem with the memory banks. The same is here. If you measure here also the 40 ohms, and if not, the memory bank A or B is faulty, and then maybe you have to replace the RAM ICs. Also, this voltage regulator only generates 1.35 volt when you power on your console. GDDR6 is a type of memory that is used in the PlayStation 5. Impedance is an important factor in the GDDR6 memory design. It ensures the signal integrity and also ensures that the data transfer can go to a high data rate. The impedance of this memory type is usually around 40 ohms. This impedance is chosen to match the transmission lines on the memory module and the memory controller, which helps to minimize the signal reflection, distortion and other signal integrity issues. Matching the impedance of the memory with the rest of the system is essential to ensure that the data can be transferred efficiently without any errors. So low impedance helps to maintain a good signal integrity and also is crucial for high-speed data transmission. When you measure the resistance on the output of these coils, it should give a reading of 40 ohms. If it is much lower, then it's an indication that you have a problem with your RAM modules. Then you have to remove your RAM ICs to see which IC is faulty. The SSD controller and the NAND memory are located in this region. The SSD controller needs power to operate. So on the back side of the board, there is a voltage regulator that will create power for the SSD controller also. The input is 2.5 volt at this cap, and at the bottom of this cap there should be a power generated of 0.8 volt. The input voltage of 2.5 volt and the output voltage of 0.8 volt, these voltages are only created when you turn on your console. In this region on the back side of the PCB, there are some standby voltages present and also some power on voltages. So when we zoom in on these pads here, there should be 1.35 volt present when you power on your console. So this is the Vmem memory. When your console is in standby mode, when you measure your voltage on this location, on this pad, it should give 12 volt. Also the connector here should be 12 volt. On this resistor here for the data line, for the power data line or the eject button, is 3.3 volt standby. Same is here. So on this pad here we should measure 5 volt, and this 5 volt will only be present when you power on your console. This is the SSD controller IC. These are the NAND flash memories. This SSD controller fails a lot. You can replace this IC. This IC is also a expensive IC to replace. To get the console into safe mode, what you have to do is you have to press the power button and keep the power button pressed. And eventually, if the SSD is failed, it's a possibility that you can go into your safe mode screen. But then you know that the PlayStation 5 is fine, but there is some issues in this region. This is the SSD controller circuit. When you connect power to the PlayStation 5, there will be a boot sequence started. So in the case there is a current draw of 175 milliamps and jumps back to 10 milliamps, that can be an indication that you have a bad SSD control IC. There's a little trick that we can use to try to isolate the problem. What we do is we set a multimeter in current mode in series with the pads. So one probe goes to the first pad of the fuse and the red probe to the second pad of the fuse. And then you measure the current draw. So when you connect power to your PlayStation 5, there will be a current draw, and in a good working circuit, the current draw should be around 310 milliamps. So if you see a different value, so a different current draw, that can indicate that this circuit is faulty. This is the brain of the PlayStation 5, it's the APU. The APU in the PlayStation 5 is a combination of a CPU, so a central processing unit, and a graphical processing unit, also known as a GPU, and both are embedded into one single chip. The APU in the PlayStation 5 is responsible for handling the console's computing and graphical processing tasks. When the APU dies, you cannot replace it because the APU is married to the board. And also what you can see is all the data lines are going directly to the GDDR6 RAM modules. Also the data lines to the SSD and the NAND lines are going directly to those memory banks. When you have a pulsating blue light of that and all the voltages are present, all the standby voltages are present, all the impedance measurements are okay, yeah, most likely the APU is bad, or the RAM modules. There could be some solder balls underneath the APU that are broken, or maybe some ripped traces. The best option is to reflow or reball this APU and to see if that resolves the problem. If the problem stays the same, then you could try to reball every RAM IC and measure them. This IC here is called the USB-C redriver or retimer IC. So when we zoom in, this is the IC. This is the pinout. The USB Type-C redriver or retimer IC is a specialized IC used in USB Type-C connections to improve the signal integrity and extend the reach of the high-speed data transmissions. And this IC often fails also, so this IC could be faulty, so check all those pins for shorts. This is a 3.3 volt battery, and this battery is used to power the real-time clock. This battery is responsible for delivering the power to the real-time clock, because the real-time clock needs to generate a 32 kHz frequency for the Southbridge. So in a case that this battery is empty, you should be aware that there is a possibility that the Southbridge is faulty, or there is a component is on the power line of this battery is shorted, or maybe a resistor is out of specification. Because if the battery is empty, this means that the battery is drained by a short. On the backside there is a 1K resistor and a Xenon diode. So if the resistor is off specification, it could also drain this battery. But most likely the Southbridge IC is shorted, and because it's shorted, it drains this battery empty. When you can't update the PlayStation 5 and during the update process or after the update process, the console starts rebooting, then the cause can be RAM related. In that case, you have to check all the RAM modules. You can use a thermal camera to see if some specific RAM module is getting hot. And if you find one, you can reflow, reball or replace it. If the problem still exists, and if you know for sure that the RAM modules are okay, then the problem could also be with the SSD controller, and the memory modules can be faulty. So this is also a difficult problem to diagnose. If you can't explain why the PlayStation 5 is giving you a pulsating blue light of death, then it's most likely has to do with the memory module, with the NAND modules, the APU. So the things that you can't really measure from the outside. The Blu-ray drive also has a drive board. This drive board IC here is paired to the APU. So they are married. So if this IC goes bad, you can't update your game console anymore. There's no disk drive support and no online gaming after the update. We cannot refresh this IC, so it's just game over. In this last slide, there's a list of fuses with special markings, and each marking corresponds with an amp code. So if you see a fuse on the PCB board that you don't recognize, you can look at the marking and find the correct amp code. If you know the amp code, you can order those fuses online. Thank you for watching this video about how to troubleshoot the PlayStation 5. I hope you found this video informative and inspiring. If you enjoyed it, don't forget to give a thumbs up and share your thoughts in the comments below. Until next time, keep learning. Bye bye.